When we're trying to predict properties of a specific matter and knowing how it's going to interact with its surroundings, we need to understand the state of matter or the phase in which it is in, because that helps us understand the interactions occurring between those molecules and how much energy is bottled up within those compounds. Gases have interactions that are minimal because they have the most amount of energy, so they are moving around, and they may have instantaneous interactions if they collide and then move on, but there's nothing really keeping those particles together. Liquids have less energy and they're flowing, and with their flowing they're still passing each other, but they are going to have some stronger interactions between the separate molecules or particles, whereas solids are tightly packed particles that maximize the amount of interactions and create that kind of lattice structure. Remember, molecular compounds are covalent compounds. They are nonmetals and they are physically bonded by sharing those electrons. The set ratio, or the subscripts within that formula, is the set number of atoms per each molecular compound. But when you bring a bunch of those together, you're going to have a large number of atoms. For that force of attraction that allows us to see water, to see glucose or sugar, we have to understand the forces that bring the separate molecules together and interact. And that is called your intermolecular force. So the intramolecular force is the physical bond. The intermolecular force is weak, and it's what attracts separate molecules together. They're weaker than bonded atoms, which means they can break easier, which is why molecular compounds have the lowest melting and boiling point out of all the types of solids that exist. We're going to go through each of the types of intermolecular forces, starting with the weakest one. Dispersion, also known as London dispersion and sometimes van der Waals forces, is the weakest of four that we are going to talk about. How this is caused is it's going to create what are called instantaneous dipole interactions. From polarity, you should remember that for a polar molecule, you're going to create that slight positive and slight negative charge based off the pole of electrons on the electronegativity of each atom within that bond. However, when we have nonpolar molecules or just pure elements, they are not polar. What allows them to change state of matter? So if you have nonpolar, there's no attraction between separate molecules. And if you don't have that attraction between separate molecules, it would always be in the gaseous state. But as we know, covalent compounds can go into a liquid and a solid if we remove enough energy. But in order for that to happen, there has to be some force of attraction. All we need in that dispersion is the electron cloud. The electrons, because they're constantly moving within that electron cloud, can create that instantaneous dipole by shifting to one side or the other. So what happens here with pure helium is the interaction of one helium to the next can cause that instantaneous dipole to be formed. And so when that slight positive one helium atom is formed, it's going to force the other helium atom to have a slight negative. And this is going to be your induced dipole on atom A. And so this can occur when you reduce the kinetic energy enough to force the atoms closer together and create this induced dipole moment. But this is going to occur at very, very low temperatures. Within a molecule, same thing. If you have a non-polar molecule, you don't have that distribution of electrons, that unequal distribution, so we need to force it. Just like we did with helium, as they start to come together closer and interact, the electrons are going to shift in those electron clouds because they're all negative and they're going to repel each other. So one of the molecules is going to generate a slight positive charge, and that's that instantaneous dipole moment, and it's going to force the electrons in the other cloud to move, to be attracted to that positive, creating that slight negative. And so then you get that induced dipole moment. All covalent compounds have dispersion forces because they all have electrons. However, the amount of electrons you have will help increase those instantaneous and therefore induced moments to bring together and change state from gas to solid, liquid or solid. So the larger molecule will have, the more electrons. The more electrons you have, the stronger that instantaneous dipole and that induced dipole is going to be. So you're going to create a larger force of attraction between separate molecules. And so when you have that larger force of attraction, you're going to see that phase change. And it's going to have that difference of that melting and or boiling point. The middle, or the second force, is a dipole-dipole. What occurs here is you're going to have a compound that has permanent dipoles within it. So that means there's an electronegativity difference that is occurring within that compound. So you're going to have a permanent slight negative and slight positive charge. Dipole-dipole is stronger than our dispersion forces. So we talked about our dispersion. And all molecules have dispersion. They can all create instantaneous and induced dipoles. But if you have a compound that already has permanent dipoles, so you have a permanent slight negative and positive charge, you move on to this interaction of dipole-dipole. When you have this, the atom with the smaller electronegativity is going to have that positive charge, and it's going to be attracted to the slight negative charge on a different molecule, and you're going to get this force of attraction between these two. There's no physical bond. It's like magnets. You can't actually see the magnetic force between two magnets, but it's there. Same kind of concept. You will get some repelling when you have the positive with the positive, but overall you have a lot more of this attraction than you do with the repulsion. So this allows the molecules to come together tighter. So a molecule of dispersion has the least amount of energy that is required to separate them, because you just have to get those electrons to move away, the molecules to move away. In dipole-dipole, you have to input a little bit more energy to physically separate those slight positive, slight negative charges. These charges are nowhere near the strength of ionic compounds because those are a full transfer of electrons, but they still have that slight attraction, so we need to pump more energy in to break or interrupt the interaction that is occurring. Now, not all of our substances are just pure molecular compounds. What happens when we put sodium chloride in water and the sodium ions are attracted to water and the chlorine ions are attracted to water? How does this happen? How can we have this interaction occur? Well, this is called an ion-dipole interaction, because the ion is going to come from that metal or non-metal. And it's going to create a dipole or an attraction to the covalent or molecular compound that is in there. So we have this neutral species, which is our molecular compound. We can have that ion-induced dipole. So this positive charge is going to force the electron cloud to shift in order to be attracted, right? So that is what we're looking at here. We already looked at what creates that dipole-induced dipole with the dispersion forces. But with here, if we have our cation, so that positive charge is going to be attracted to the negative side of that polar molecule. And it's going to be repelled by the positive side. So this is like water. So when we have a sodium ion in water, the oxygen side, the slight negative, is going to be attracted to the sodium. And it's going to force away the slight positive side of the hydrogens. And so this helps explain how we can dissolve ionic compounds into polar substances, is because we do have that slight positive changes. So we have started with our dispersion forces, which require only the presence of the electron cloud and the movement of those electron clouds to create that instantaneous dipole interaction. Then we have built up to the dipole-dipole or that ion-dipole interaction, which requires a polar molecule for a higher energy interaction. Then we end with this highest energy interaction, hydrogen bonding. So hydrogen bonding is the strongest. For a compound to allow for hydrogen bonding, you need a compound to have a hydrogen that is directly attached to nitrogen, oxygen, or fluorine, not any other element. These three allow for the largest discrepancy in electronegativity, that you have a really strong slight positive and slight negative. For the most part, it's close enough to creating an ionic interaction. When we represent hydrogen bonding, we will actually use dotted lines to represent the strength of that force. They have found that hydrogen bonding is about 5% the strength of a covalent bond, so not a bond in and of itself, but it is the strongest force present and dictates a lot of properties for some compounds. So on water, so here we have H2O, the hydrogen on one water is called the donor, and the oxygen of a different water molecule is the acceptor. So this oxygen is accepting the hydrogen bond from a different water. Within one compound, as long as that one compound has that oxygen or the hydrogen bonded to one of those three elements, you get that hydrogen bonding. You can also have hydrogen bonding between different molecules. You need a lone electron pair that can act like oxygen does. It's acting as that slight negative. So it wants to be an acceptor, a hydrogen acceptor. And then you need to have like water or NH3 or HF, you need to have the molecule that has that hydrogen bonded to one of those three elements. So an example being is if we have our water has its very strong slight positives, slight negatives. And let's say we have formaldehyde. So this oxygen on formaldehyde has a lone electron pairs, so it can act as a hydrogen bond acceptor. So the hydrogen on one water species can form that hydrogen bond between the water and the oxygen of the acceptor. It's not going to be as strong as within one molecule, like all water molecules, but it's still there. The reason it can't be as strong is that formaldehyde itself cannot also form hydrogen bonds, but it can accept hydrogen bonds, just not donate them. So we have those two interactions between the same molecules and a different molecule and water, how hydrogen bond can be formed. Again, what you need to be able to identify is, do you have a hydrogen bond acceptor? So that's going to be a nitrogen, oxygen, or fluorine, or something with lone pairs. And do you have the donor? That is where you have the hydrogen that is directly bound to an oxygen, nitrogen, or fluorine.